Welcome to the tutorial session. In this session, I wanted to give you a sense for some of the new modern approaches to instrument analysis and how to model instrumentation and so on. Okay, some of this is something which I have worked on and published, which is an award-winning paper from a few years ago. So basically, the goal here is to analyze any optical instrument. What's the general process to doing that? So this uses a new notation and kind of I'll talk about the notation and also the basic ideas. As long as you understand the ideas, like the notation, it's likely that you're seeing this notation for the first time, so that may look a bit difficult, but like once you get used to it, it's actually much simpler. Okay, so the basic idea behind this way of analyzing things is you build a system just like you make a good strong connection between theory and experiment. What do I mean by that? So let's say you have an optical table, meaning a table where you are setting up the instrument, and you put one component after the other component after the other component. So just like you put them and then put the next one, you just put together the theory, like every component and every light propagation or any other, like whatever happens is described by what's called an operator. Okay, it's an operator notation. So every component has its own operator, and just like you put things together on an optical table to build the instrument, you put together the operators to build the theory. So there is a very good direct connection between the experiment and the theory, and this way you can kind of understand like the theory much better. Okay, so here is the basic idea behind this approach. So you start with a source, and then light travels onto a beam splitter. It splits this way and this way, goes to one mirror, goes to another mirror. This is just a simple interferometer. Then light comes back from this mirror, light comes back from the other mirror. Then it goes to a lens or a cassette ray, like a lens focusing system, goes to the sample, and then goes to the detector, and you make a measurement at the detector. Okay, so this is like a general what's called a FTIR imaging system. We'll get to this like what the instrument does in tomorrow's class, at least some of the things. But this for any instrument, even OCT instruments, this is the same principle. So you can use this method of analysis. What does this do? As I mentioned, what it does is basically it's like uses an operator. So let's start with a field here. So I use like this kind of a strange notation where so you have a line like this. Okay, a variable, a bracket, like a square, a triangular bracket of this sort. So this is called the bracket notation or Ketra notation. And like it actually, so like this, and there is this, and you put them together. This is called a bra, and this is called a ket, and we call it bracket kind of notation. This is actually kind of also called Dirac notation. So this is used in quantum mechanics or physics. People who do physics use this often, but in optics, like this is useful. Like I'll show you how this is useful. Okay, so start with source of light, which has some kind of some field associated with it, and then light propagates. So you have an operator for light propagation from this position V0 to Vi, V interferometer. Okay, the location. Then you have light travels from the interferometer to by distance D1 to the mirror here, and then light comes back, and then light goes this way and D2 distance D2 and comes back. Okay, and then it goes through like a focusing system and onto the sample, and then it goes through the field immediately after the sample is this, and then this goes to the detector, and you have the field at the detector, which is UZD. At the detector, what's the field? And then at the detector, you make a measurement. Okay, so this is basically, so what I'm trying to convey to you is, take every component, describe it by an operator, and just like you put together the components on an optical table and build the instrument, you put together the operators and build the theory. And at the end, you get the data. And what you get at the end of it is the connection. There is S, which is a sample here, and data, which is the ZD, which is, you take the intensity of this, and all the other things, all the other operators tell you is because of the instrument. Okay, so it connects the data to the instrument to the sample. So if you from the sample you get data, in between there is the instrument, and the instrument is described by these operators. And what we are trying to do is go from the data back to what the sample is, by just undoing all the like what happens in between. And this is how you think about. There's a newer way of thinking about how the instrumentation works. Okay. Yeah. So here is kind of like the basic idea in Dirac notation. So a field is described by this entity of cat, which is like u at the location z, right? Like the field is traveling in z or z direction at any point z. The field uz is given by this variable. Okay, and this is if you want to figure out what its value is. So the thing is this one. It's like, what is it a function of? That is like that question is a bit kind of so this can be a field in any kind of space. So if it is an XYZ space, then you project this field onto the XYZ space and you get the field in XYZ coordinates. Okay. If you project it onto the Fourier axis, you get fx, fy, fz coordinates. So it's a field. You can describe it in XYZ coordinates, or you can describe it in fx, fy, fz coordinates. So if you describe it in XYZ coordinates, what's the field at that plane in what's the spatial distribution? This is u of r. What is the spatial frequency distribution? Then it is u of r and u of r. Okay, so all of them, like you take the field, project it on the r on the r axis or r coordinate system. Take the field, project it on the f coordinate system. You will get the field in the Fourier domain, whatever the field is. Okay, in the spatial domain. So if any domain, you can get the field. So that's the kind of one of the advantages of using this kind of f as the spatial frequency domain. Okay, and this is the other kind of the Hermitian adjoint. So it's so if you take u and uz and uz and put them together, uz and uz, put them together, this will give you the intensity. So it's like u squared, magnitude squared, so it gives you the intensity of the field. So if you make a measurement, the process of making a measurement, so like it's analogous to in quantum mechanics, you make a measurement and it collapses the wave function, right? You make a measurement, like when you make the measurement, you see what the value is. Similarly, this one, you take the field, you do this you bracket, and then it becomes an intensity value. It's the measure, whatever you measure is that. Okay, that's the idea. Any questions so far? Okay. So now the goal of the entire instrumentation is to measure the field at the detector, UZD. At the detector, what is the field? You want to relate it to the sample S and A, which is an operator, which is the entire optical system. Okay, so we will figure out what A is. But at the end of it, it's a simple equation. What you see at the detector and what the sample is, it connects the two with this operator A. Okay, so that's really all we are doing with this kind of an approach. Okay. So let's start with some simple stuff. how does light, say you know the light wave in one plane, what happens as light travels to another different plane. So as light propagates, it can be described by a propagator PD at a distance. Light has traveled a distance d. PD is the operator that takes the light in one plane and gives you the light in the other plane. And the way to think about this is the equation for light propagation. So let me explain what this means. So it's something which, like, so this says take a Fourier transform, then multiply it by this function, then take the inverse Fourier transform, and then you get the, like if you in spatial domain, you get that. That's one way to think about it. Or in other words, if you go from the Fourier domain on one side and Fourier domain on the other side, all you're doing is multiplying by this phase factor. So what happens if you know the field in one plane in the Fourier domain, as light travels, it accumulates a certain amount of phase. That amount of phase is this one. In the Fourier domain, the other side, only thing that has happened is light has accumulated a certain amount of phase. That's really all this equation. Although this looks complicated, and if you see it for the first time, it's kind of like bit difficult. But all this is like the inverse, the way of thinking about it is, this operator takes a Fourier domain, like takes a certain wave which is going in a certain direction, takes it to the other side. It continues to be in the same direction. It's the same direction, and all it has done is accumulated some amount of phase. Amount of phase is basically proportional to the distance d in the exponent, right? In the theory, e to the I 2 pi f3 times d. So it has accumulated a certain amount of phase. So this is how you think of like light propagation. And one of the properties of this kind of an operator is that if light travels a distance d and then d prime, it's equivalent to distance traveling a distance d plus d prime. Intuitively it will be clear, right? Light travels from here to here and then here to here. So d and d prime is equivalent to distance traveled. It has entire distance d plus d prime it has traveled. So that's kind of there's an equivalent. So this is one of the properties of this kind of operator. Okay? So I started with like the source here, and I basically apply this operator. So what we have done is taken the light from the source, propagated to this beam splitter with this K operator. You can do the same thing at the splitter. What happens? Light travels a distance T01. So it travels a certain distance in this plane, this direction. The entire thing, all that the interferometer does is splits it into two. Let's say it's 50-50 beam splitter. Splits it into two. One travels a distance 2A1. Like why is this 2? Let me show you that next, okay? So it travels 2DA1 and 2DA2. Okay, so let me show you why. So light travels a distance d1 and light travels a distance d2 here, right? Light comes back here, and this is another d1. So d1 forward, d1 back, so 2d1. And then similarly d2 here and d2 back, so 2d2. So and then there is a 50-50 component, right? Therefore what you have is 2d2 and 50-50, the 50-50 over here. So that's what the interferometer is doing. And so then you have the light send it onto like a focusing system, and it could be a lens, it could be something like a lens, something equivalent, and then it goes to the sample. So it focuses on that light onto the sample. Okay, so that's the next step in the process. And so this can be given by this operator G1, this focusing mechanism. So in fact, this is called the simplest kind of thing that focuses light is a lens. So if So one of the problems with lenses is that if you have light of one wavelength, it's okay. But if you have light of multiple wavelengths, then like this, because if it's made of glass, then red is focused one place, green is focused another place, blue is focused another place. So different colors can focus at different locations. So that is called dispersion. So that can be a good thing if it's a prism or a grating, but it can be a bad thing if it's a lens. You want all wavelengths to focus at the same location. So it might be hard to get a lens of that sort, especially in infrared, for example. So when there are long wavelengths, like large range of wavelengths, in electricity system, you need a big range of wavelengths, right? All wavelengths have to be focused on the same spot, which is really hard to do. So in that kind of a situation, what you do is, instead of a lens, you use a pair of mirrors. Mirrors, the advantage is angle of incidence is equal to angle of reflection. Doesn't matter what the wavelength is. So all wavelengths travel the same direction, the same path. So you can use pair of mirrors and do kind of focusing, and that's called a Schwarzschild Cassegrain. Okay, so this was invented for telescopes that's a long time ago, and in fact Newton was one of the first to figure out that, like in a telescope, if you, instead of using a lens, Galileo had made a telescope with lenses, and Newton kind of figured out that instead of a lens, if you use a mirror, parabolic type mirror, then you can see much clearer, the stars much more clearly, and so on. So, and then Schwarzschild and Cassegrain and other scientists later on made the kind of much higher quality, higher like better and these systems. Instead of one mirror, you use two mirrors, or kind of, and so that is useful for a lot of infrared, mid-infrared, near-infrared kind of imaging. So this is what's called a Schwarzschild or a Cassegrain system. And then light goes through and hits the sample, okay, and then it goes through the sample. So so this can be thought like, so this focusing can be thought of as light from one plane onto this lens D1, and then it goes with an operator G, and then another D2. It goes through a distance D1, goes through the lens of Cassegrain, and goes through a distance D2. That is the like object plane to the image plane. So that is the process of focusing light onto the sample. So that's basically given by this kind of an operator. So then in fact this is such that 1 over D1 plus this is 1 over D1 plus 1 over D2 is equal to 1 over F or LF in this case, right? So this is the lens equation which we have seen before. So even for although this is not for a lens, this is for a Cassegrain, the same type of equation is valid for this as well. And then there is also the second thing, which is magnification. So if D2 divided by D1 is the overall magnification of this lens system or a imaging system. So you magnify the kind of, if you want to see something small, you use a magnification so that you can see small objects with this. Okay. So this is light propagation through a Cassegrain or Schwarzschild. So this is how this works. And so you put them all together. Light here goes to the interferometer, then goes to the interferometer, goes towards the interferometer, then goes into the interferometer and kind of goes back and forth, and then goes through the focusing system, falls on the sample. Once it falls on the sample, it interacts with the sample. So this is for light sample interaction, light matter interaction. So there is another operator. This looks complicated, but it's actually kind of a simple multiplication. In the spatial domain, it's a simple multiplication. So light comes in. In some places, light gets absorbed or scattered. Some places it doesn't get. So all this is saying is light goes through the sample and gets interacts, and like just after the sample, if this operator is incident on the sample, just the field after the sample is given by this kind of an expression. So this is the operator. So the thing is, these are like standard, just like these are standard optical components. You could buy a lens and put it there, buy a this thing. So people have already figured out when light travels, this is the operator. When light goes through the system, this is the operator. So you just put them together, just like you put components together to build a system. You put these operators together to build the overall theory. And that way it's a modular kind of, you can instead, if you say, for example, next day, you say, I don't want to use this length, I want to use some other kind of a length or something. All you need to do is remove that operator, put a new operator in, and everything else is the same. So it has that additional convenience for like theory. So this is like sort of what is happening. The light source is here, it goes to the, let me use. See, light comes here, splits into two, comes back, this is the interferometer, it goes to a focusing system, goes to a sample. Just before the sample, this is the field, just after the sample, this is the field, then it propagates through one more kind of focusing system and another focusing system, that is incident on the detector. Okay, after you do all this, basically light in the detector you can figure out. If you just put them, just do the math and put them all together, the expression may look lengthy, but in principle it's just simply putting together all the different pieces. Okay, so it's much easier to visualize it graphically or through animation. Field from the source is going to the interferometer, is going to D1 and D2, and that is the interferometer, is going to a focusing system, falling on the sample, going through the sample, going to the detector. And all we have done is figured out, use D as a function of the sample and everything else. Okay, that's basically the idea. So yeah, so yeah, so this is where so this is where I wanted to give you an exercise to do in as a part of the work like this tutorial. I want you to kind of figure out the light propagation. So I want you to take this light propagation operator and do, if you have a plane wave incident on this at one plane, if you have a simple plane wave which is perpendicular to the kind of z axis or along the z axis, if it is falling, propagated by a distance d, sense for how to do it. As I said, the way this question is, there is a field u at the starting point which is given. The field u in xyz coordinates is just 1. In that plane it is just one just constant. Okay, if an operator kd is acting on it, it makes it travel for a certain distance d, and you want the answer in xyz coordinates. In the plane after it has traveled a certain distance, what is the value of the field in that plane? That's what you want to do. Okay, so so what you will have to do is in this equation over here. Yeah. So in this equation over here, what you have to do is to apply u here, and here you have to do r. Okay, so f acting on u. So what does that mean? F acting on u is equal to, what is the Fourier domain field? In the spatial domain, if it is 1, what is the Fourier domain here? What's the Fourier transform of 1? Sorry? Delta of f in this case. Right? So, so therefore, in this location, apply delta of f. Okay? The other thing is r acting on f. It is e to the I 2 pi f dot r. Okay? That's this. So you have r acting on f over here. So this is, sorry, yeah. So this is here, f is here. So all you need to do is solve this integral and figure out what the answer is. Okay, so this is how you think about this question. I'll walk you through this again one more time. but I just wanted you to try working out the integral and see if you can figure it out. Okay. Although it is in 2 dimensions, like everything, whatever you learn for 1 dimension will also be exactly the same for this particular example. Okay. So let me write this in this line. Is T01 is integral e square f e to the I 2 pi f dot r and e to the I 2 pi f f d of f d delta of f. Okay, you need to figure out this integral. Shall I say that again? F not f, fx is called direction. It's a Fourier dimension. So you're integrating along the Fourier axis, fx is y axis. So there is, notice that there is a delta function and there is an integral over in the space where there is a delta function. So if you remember what happens, how do you integrate when there is a delta function? That's a hint as to how to do this. Okay. Yeah, anyone remember how to do integral when there is a delta function involved? Exactly. Yes. So repeat, like those who didn't hear that, it's called the sampling theorem, or like so basically, uh, uh, like so whenever you have a delta function inside an integral, everything other than the delta function, take that and substitute where the delta function becomes like non-zero. Plug that value into the rest of the function, right? So that's how you do it. So yeah, let me show you. So there is delta function is at f equal to, so delta function delta of f is non-zero at f equal to 0, right? And what you have to do is take the rest of these terms here and just substitute f equal to 0 in here. That's it. When you substitute f equal to 0, you get, so the integral goes away. You get e to the I 2 pi 0 times r times e to the I 2 pi fg of 0 times t. Okay. What is 0 times e to the 0 times r is what? E to the 0, right? What is e to the 0? 1. So this becomes 1. This is fg of 0. What is fg? Fg equals square root of u square minus fx square minus fy square, right? So if this is 0, this becomes just mu, right? So what happens is this one will become e to the I 2 pi mu d. Okay? This is basically a final answer. So what am I saying? Let me kind of say it in words, okay? So there is a field which is a constant in one plane. It travels a distance d. Here it becomes a constant just because accumulated some amount of phase. How much phase is it accumulated? 2 pi nu times d. That's all. So therefore, it's still a constant. It's a new constant which is an additional phase. That's it. So plane wave has traveled the distance d and accumulated this amount of phase, and that's how light is propagated. That's so. Although it looks complicated, the principle is quite simple. Constant becomes another constant. It has accumulated extra phase, and that's in fact the magnitude of this is also 1, right? E to the I something is e to the I theta magnitude is also 1. So it's still a constant in magnitude. The phase is some value, which is an increase from the previous one. Okay? Any questions? So this is how you think about the problem. Okay? So that's, yeah. So the next thing I want you to do is, instead of a plane wave which is constant, if it's a tilted plane wave, it's slightly tilted, so it's coming at a slight angle, then what is the answer? Okay, so this is something I want you to figure out, and this and the Gaussian will ask you. You can pause the recording for now. Yeah. Okay. So I'll be here for a few more minutes, but if those of you online, if you want to, I'll show you what to do in this problem. But I want to give you a minute. So we do the same thing that we did in the previous one, except for the field is slightly different here. Okay, it's a tilted plane wave instead of a regular plane. Correct. Yeah. You understand what's going on? Okay. Are you able to get what's going on? Yeah. Mm-hmm. Show me what you do. Okay. 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 Yeah. Keep going. Do have a Do you think what's going on here? Yeah. That's the 2 year transform T01. Hmm? Let's see. Try this. Okay? Let's see if we can figure out this. Hmm. It's tilted. The tilt is given by S0 or like how it is tilted is given is indirectly given by S0. Okay, so you are not given an angle, but you're given F0. So use the F0 and like I understand what you're saying theta, but the theta is decided by F0. Yeah, because it's a two-dimensional thing, right? Theta is it like this? Theta can be at different angles. Right? It's like a cone, right? Any theta can be which direction. So this F0 tells you exactly which direction. Two-dimensional, right? It's a vector. Hmm. It's not just an angle, but also yeah, two angles. So a hint here is that so this is what is f u that f acting on u, which is in the Fourier domain. So if you take so e to this is of the form e to the I fx. So this is take the Fourier transform of this, you will get delta of f minus f0. Okay, so it's a delta function, but a shifted delta function. So this is one of the hints that you can use, and from this, let's see if you can figure out. Anyone online has a question? Or? Sorry? Oh, okay. Mm-hmm. You are turned off? Sorry. Yeah, okay. U here and put R here, right? So basically, you want to find the same thing as before. You want to find the field traveling a distance d and in xy space. So this f acting on u is just delta. So you substitute delta of f minus f naught in here, and this one becomes e to the I 2 pi f dot r. Okay. Again, there is a delta function inside an integral. So when you have a delta function inside an integral, what do? Use the same idea. Okay. Whatever we did in the previous case, whenever you have a delta function inside an integral, what do? Do the same thing. Use the sampling theorem. Have you seen the sampling theorem before? Whenever you have a delta function inside an integral, what to do? Have you seen that? Or? Yeah. Are you able to get there? Yeah, you have to, yeah. So let's see if we can solve this particular one. In terms of solving this problem. So whenever you have a delta function inside an integral, you look at where the delta function is non-zero. Here, f equals to f0, right? Substitute f equal to f0. Whenever you have f here, substitute f equal to f0. That's the answer, okay? So in this case, look at this expression over here. Substitute f equal to f0, you get e to the I 2 pi f0 dot r, okay? And take this one and substitute f equal to f0, you get e to the I 2 pi fv of f0 d, and that's your final answer, okay? So basically all you need to do is take this. So what this is saying is, if you start with e to the f0r, e to the I 2 pi f0r, it accumulates the phase of e to the I fv d. That's it. Okay, so it has, you have a plane wave, it has accumulated a certain amount of phase corresponding to e to the I fv d. So graphically, the way to think about it, if it travels a distance d, then if this is initially a plane wave this way, it is this plane wave, except for there is an additional e to the I fv d, it has accumulated some amount of phase. That's it. Okay, that's how you think about it. Last thing I will not do it here, but the Gaussian beam, if you have a Gaussian for a beam, then you do the exact same thing, just like what we did right now. And Fourier transform to Gaussian is a Gaussian, so you can do this. Okay, so let me stop here. I'll let you do this right now. You can. And yeah, so this is the Gaussian becomes bigger and bigger and bigger as we go along. I hope you can try to do this mathematically. You can stop. Oh, all right. That's it for today. Like I know that this was new and very different for all of you, so I don't expect that you kind of do it quickly or do it easily. But like this is just kind of like a new way of looking at things, and I just wanted to give you a flavor for it. It looks difficult, but once you get used to it, it's actually quite simple. Sorry? Right, yeah. It's simply like, okay, all the thing is light accumulates space. It looks mathematically messy, but in words, it's very easy to think, oh, it's just accumulating e to the I kz d. That's all. That's all light is doing. That's what we are saying. Okay?